All right, so today we have two research scientists from Google, Jinsung Yoon and Sercan Arik, and we're here to talk about their interesting new project called EHR-Safe. So, gentlemen, welcome to the Data Exchange podcast, and in the case of Sercan, welcome back.
Thanks for having us.
All right, so EHR-Safe, EHR for our listeners stands for Electronic Health Records. So let's go start at the basic here. So whoever wants to answer this question. So what constitutes an electronic health record? Because I think that most listeners by now, at least in the US and the West, when they go to a doctor's office, there might be a online portal or even a smartphone app where they can check on their records. So what exactly goes into an electronic health record?
So electronic health record consists of various information. For instance, let's assume that we are assuming a patient in hospital. When they go into the hospital, their vital signs such as heart rate, blood pressure, those things are regularly checked up. Those are also included in the EHR. And also, if doctors think some of the lab tests is needed, such as creatinines or hemoglobin type of stuff, and then they do the lab test, and then the results are also included in the EHR. The last kind of component is that, for instance, doctors diagnoses some disease to the patient. That diagnosis code is also included in the EHR data.
So, Serkan, are we talking mostly structured data?
Yeah, so most of the healthcare data might be considered as structured, but as we know that there could also be unstructured data, such as visual data like X-ray or CT scan images, or text data such as doctor's notes and so on. So most of the healthcare data analytics have been focusing on structured data, but now with the recent advances in visual and text deep learning, now there's also more interest in more multimodal EHR data.
So can you describe the specific problem you were solving, and in particular, maybe start with what motivated the project? Was it a specific group of let's say healthcare organizations that approached you, or is this mostly just kind of a toy project?
So we know that in healthcare industry, data access is very challenging, and there are very strict requirements for privacy. And we also know that healthcare data could be very valuable for machine learning development for improved healthcare systems. So we wanted to provide a solution where the data holders, in which case it could be like the healthcare institutions and so on, could share the data with the data consumers who can build useful things with this data. But because of the privacy constraints or the concerns, such sharing is very limited at the moment. So we wanted to provide this solution where instead of sharing the real data, very similar or synthetic data with very similar characteristics can be shared, and it can still provide these useful capabilities. So in a way, the advances in machine learning or data analytics can be unlocked in healthcare domain in much faster way. So this is a very general canonical problem that we observe to be very important in healthcare across different institutions, countries, and so on, and even beyond healthcare. Like if you think about this general setting, the data privacy is important in many other industries as well. Like, for example, there are strict regulations in the US about financial data or in public sector and so on. And we know that the data can be very useful to build improved analytics or predictive machine learning functionalities that can be used to advance the state-of-the-art in those fields. So as Google Cloud, since we are focusing on like building useful enterprise AI solutions, we thought that this is one important direction that we should address. And obviously, we have also received interest from different major enterprise healthcare companies in this.
So Jinsung, so the scenario that Sercan paints is you've got the data originators or suppliers on one side, and then you've got maybe a pool of talent here, machine learning engineers, developers. So what you essentially tried to build was a way for the suppliers to interact with the talent without violating privacy or even specific regulations like HIPAA.
It's definitely true. So what we are trying to do is we are communicate with the data holder, which is private data holders, and then we using this private data to train our models and generate synthetic data, which are very similar with the original data in terms of the statistical characteristic. But we do not include each of the patient information, but we just have the general statistical characteristic of the data in a synthetic data, and then this data provider can share this synthetic data instead of the original data to the multiple talent that you said, that they can develop the model based on the synthetic data, and those models are working well with the synthetic data, which has almost the same statistical characteristic of the original data. So we can even directly utilize the developed model on top of synthetic data into the original data. So that's our main objective that using these kind of synthetic data tools.
So let's talk about the specific implementation you guys had in the paper. So Sercan, what sort of electronic health records did you assume you had access to? And how did you test that your synthetic generator was sufficient? Or another question is, how did you know the use case, right? So how did you, right?
So we said that electronic health records might also contain multimodal information, but in this work, we specifically focused on structured data because that is the broader use case at the moment, and we started to push the state of the art in that. And structured data might be in very different forms too, like there could be time-varying data, time series data that might be numerical or categorical. So if there's some measurement, it might be numerical, it might have continuous values, or if it comes from like some discrete set, it might have categorical values. There could be some static data that does not change on time, like for example, someone's gender and so on. And again, like there could be numerical and categorical variants of these. And there could be a lot of data challenges in practice if we consider the real world EHR data sets. Like the data might be very sparse, it might come from skewed distributions, or there might be a lot of number of categories and so on. So what we had in mind was we want to develop a set of methods for synthetic data modeling that can address these real world EHR challenges in an effective way. And if you look at the most academic data sets where these...
By the way, Sercan, before you continue, so for our listeners and for me, is there a universal electronic health record format?
I think that it is mainly country dependent.
Okay.
I mean, obviously, there are some standard features. So one thing is, I think in the US, it's more or less standardized that like different healthcare institutions might be using similar software systems and similar column names and so on. And there are like some standard formats that...
So you, in this work, you targeted kind of some common format.
We use public data sets in this work, so we did not focus too much on like the software systems to extract data to put it in that format. Like that's more in the scope of the product itself, but like this work is obviously about the machine learning methods beyond that data formatting.
Yeah, and one thing that I can say is that in US there is called FHIR standard, which is how these electronic health recorders save. They are trying to make a standard of how to save this electronic health record, but not all the hospitals are participate. So we cannot assume that all the hospitals that follow these FHIR standards. So we need to make more generous system that can be applicable multiple different format of the data. Yeah.
So what use cases did you assume you had to cover, Sercan?
So as the goal, tying back to your previous question, so we would like to generate synthetic data that would be useful for the downstream machine learning tasks. So if the data user, let's say machine learning model developer, develops a model on the synthetic data, we expect that that model would be very similar in performance when we compare it to the model that would be developed on real data. And most of the use cases might be discriminative tasks like diagnosis, like mortality prediction or disease code mapping and stuff like that. So those were some of the tasks we considered as well. But beyond that, there could also be like exploratory data analysis to gain insights about different statistics or
analytics, right? So reports. Yeah.
So that is why we also had the statistical similarity type of metrics in mind that show that the utility of the synthetic data would be similar with the utility of the real data.
So one question I have, Jinsung, is stationarity, right? So in other words, you folks had, in a specific snapshot in time, the data has a certain distribution. And let's say next week, there's a power plant that opens in my neighborhood and suddenly asthma starts showing up. So how do you account for changes in the distribution?
Actually, so what we are doing, what our objective is not capturing those non-stationarity of the time series that we are trying to predict the future. That is actually not our objective. Our objective is try to preserve the original data's characteristic, that people using this data to do something like non-stationarity problems and what can be in the future, something like they can predict it. But handling the non-stationarity is not our goal of this project. You can think like our project objective is more like, if we have a private data, we try to make some clones of this private data without having privacy issues, not handling this non-stationarity. So yeah.
So Sercan, so this set of tools addresses data privacy in the context of data sharing. So in other words, if I'm a machine learning engineer, now I can build a model without violating someone's privacy. But does this also address lack of data? So in other words, if I want to build a model that requires a lot more data than the raw data.
Yeah, it's an interesting question. So one of the use cases of generative modeling could be data augmentation. And especially like if there are some rare cases, you can generate synthetic data for those rare cases. And you might expect that it might help the model development since you have more data coverage. So one thing to note is that we are not bringing extra information, like we are given a data set and we train a generative model on this data set, and then we generate new data and so on. And you can train a discriminative model on this data set to begin with as well. So there's not that much, there's no information gain, and you might expect that because of it, the gain might be limited, but it might have some like regularization like effect that if you have some rare cases, maybe having extra data for those rare cases might improve the downstream model's performance.
Or sometimes when you're training a model, because you don't have that much data, it turns out your resulting model isn't that robust. So will this help?
Like especially for imbalanced data sets, those kind of practical training issues can be very common. That's why like even very simple tricks like oversampling rare cases might be helpful. But if you have generative model, it could be useful for that purpose as well.
So Jinsung, why now? And why couldn't we have done this 10 years ago?
Actually, that is actually a good question. So right now, as you know, there is some extremely developed generative model from 2014 and 2016 about kind of GAN models are coming out, and VAE is also coming out, and these days and the diffusion models are coming out, which means that we can we can run the generative distribution of the original data with kind of developed tools such as GAN or diffusion model. So with this development, we can also apply this kind of view on very hot techniques into this kind of EHR data, which is kind of more private data, and then we can generate more kind of similar data set in comparison to the original data due to this kind of generative model improvement. So that's the reason I think we can do more useful synthetic data right now in comparison to the 10 years ago because of this generative model development.
So, Sercan, can you quantify when he says more useful? So how much better?
Yeah, I think that for generative modeling, it is hard to come up with very exact metrics, but here is one thing. Like, for example, when you do discriminative modeling, you can quantify the accuracy of the model and maybe improve. Like, if you look at different data sets, tasks, and state of the art over time, like there are some improvements, I don't know, 1% over the best model of the last year and so on. And maybe in some applications, there is some threshold which might make it acceptable. Like, for example, if it is something like speech recognition, we know that like if it is 95%, it's not annoying. If it is 85% accuracy, maybe it's annoying, so it's not usable. I think when it comes to generative modeling, those kind of thresholds might be even more sensitive, that if the data quality is much lower than real, I think it will definitely be not useful, obviously. But if you think about what data quality might make these synthetic data useful, I think the bar for that one could be quite high, especially in fields like healthcare. So like the generative modeling capabilities we had before, I think that they were not sufficient to push the state of the art to a point where synthetic data generation was good enough to be used in real world. And I think that now we are very close to it. And we know like there are other exciting advances in generative modeling with like image data or text data and stuff like that. So I think that with these advances now, I think the field is at some inflection point that there will be more.
But Jinsung, in this context, you have access to the original data.
Mm-hmm.
So then you go about, you generate synthetic data.
Mm-hmm.
You build a discriminative model on the original and on the synthetic.
Yep.
Can't you measure how good the synthetic data is?
Yeah, that's actually kind of one of the main metric that we use in this paper, which is called train synthetic and test layer. So let's first divide the original data into train and test set. And then we only using this training data to train the generative model and generate synthetic data. And then we train two discriminative models. One discriminative model is trained on the original trained data, and the other discriminative models are trained on the synthetic trained data. And then we evaluate those two models into the holdout original data, which we never seen. And then if the accuracy difference between trained on synthetic versus trained with original is small, which means that the synthetic data is capture the feature label relationship well in the original data. So we use this train synthetic test layer setting to check whether the synthetic data is realistic and more useful when we kind of make a discrete model on top of synthetic data.
Now, is it possible for the trained model on the synthetic data to be better?
You would expect that it would be similar, like maybe it might be slightly better because of randomness or other like deep things of deep learning training, but it would not be statistically significantly better.
Yeah, interesting. So how does synthetic data in general, from your guys' perspective, so we talked about the benefits. So what are the limitations? So Jinsung, you can start.
So one limitation is actually the privacy. As you know, there is no standard way of measuring the privacy of the synthetic data. Of course, the synthetic data is generated from the random signal, and the random signal come into the generative models and outputs the synthetic data. So the starting point is random. So we can think that this output of the synthetic data might not have information of the original data of each patient information, but that's not enough. We need to carefully check whether seriously this synthetic data does not include or does not leak the original data, privacy of the original data. Actually, there is no standard way to measure this one. So we use 3 different metrics.
Or in the in other techniques like differential privacy, forget about measuring. They have theorems, right?
They have theorems, but one point is that in order to satisfy the differential privacy, we need to add actually a vast amount of noise on top of the model, which makes the fidelity very low.
So, but in this case, if your goal is to come up with a way to measure, at what point will a regulator be comfortable to say, okay, so you measured, it seems like it's okay, so it might not satisfy a regulator, even if you can measure it, right?
Yeah, I think that there are no written rules on those things yet. There might be more in the future. So that is why, there's a component here that you want to come up with these privacy attacks, and we show that our synthetic data generation would be robust to them to convince the users and potentially regulators and so on. So there could be, we have already worked on some privacy attacks. There could be many more that can be considered as practical and important. But at the end, there's still the open question, as you mentioned, one can always invent new attacks, and then you can work on the robustness against it. But if there are some certain theoretical guarantees that might be satisfied, it could also be preferred, but those theoretical guarantees also come with different caveats. So we have that kind of a trade-off.
So it seems like the synthetic data, the only downside seems to be this. You have to kind of make sure that you're comfortable with privacy and security. But synthetic data doesn't exist in a vacuum, right? So there's other confidential computing techniques like federated learning, secure enclaves, and so on and so forth. So where does this set of methods fit in the context of others?
One benefit of synthetic data is you might have a framework that takes the real data in and the synthetic data out. And then this might happen, let's say, at the cloud environment of the user, the data holder. And the data holder will just share the synthetic data, nothing about the real data.
I see.
So I think that there might be some practical implications of this one in the broad scheme of things, whereas things like federated learning and so on, you are aggregating data from different places, but you have different sharing mechanisms across different places.
So Jinsung, what will it take to extend what you folks have done to say text, doctor notes, or medical images?
I think that's actually a good question, and actually we are planning to extend it our current EHR work, which is only focused on time series and tabular data, to the doctor's note and the image, because the information that doctor's note has and the image has is maybe much larger than the information that the tabular data has. So we are planning to extend this one to the multimodal setting. So in order to do that, we need to adapt multiple different generative models, which is working well in text side and also in the image side. And we also need to handle some of the data shortage of the image and the text as well, because tabular data is more.
I mean, for images, synthetic data would be great for handling shortage. But Sercan, my question, Doctor Notes has, you've got what is it called? PIIs in there, right? Or identifying information, right? So like names or medication or, so you've got to somehow scrub that out, right?
Yeah, so we need to have additional considerations when we consider text data. It will definitely make the problem more challenging. And also for text and image data, we typically use pre-trained encoders and sometimes even decoders that are trained on other data sets. And those other data sets might be healthcare related data sets or other massive internet data. And when we consider the decoders, like we know that, for example, the approach we pursued using GANs, they are not the state of the art typically for text or visual data because of different challenges. So the generative modeling methodology might also require some modifications to efficiently model the distributions of text or image data. But when it comes to privacy, again, we need to maybe consider different attacks to show that, like for text data, we are preserving privacy. And if it turns out that certain generative models are not sufficient in preserving the privacy, we need to come up with like different objectives that can better guarantee satisfaction of the privacy for text data.
Yeah, because Jinsung, off the top of my head, I'm envisioning a language model, right? So a language model is text in, text out. So I put in the doctor notes. Doctor notes may have, I don't know, name, illness, and then text out. But if you take out the illness, then that's crucial information, right?
It's true. So yeah, as you know, we can also train certain models that they can identify which one is a PI and which one is a more crucial information. That, as you say, text models, doctor's notes are input, and maybe outputs are more like anonymous outputs are coming instead of removing the crucial stuff.
But so the challenge is, how do you anonymize without losing critical diagnostic information?
But here the point is that if the diagnostic information and the PIs are not connected, in that case, even if you have the diagnosis, it doesn't leak the privacy of the PIs. Yeah.
Right. But visual medical images, Sercan, should be much more straightforward. No.
I think that the challenge there is conditional generation. So when we are generating multimodal data, we want to make sure that different modalities are aligned in information. And like if we look at the generative image modeling applications and so on, like for example, for artistic tasks, you care about creativity or creating something different and so on. But here we also care about the generated image being consistent with the information from structured data and the text data as well. And doing that in a realistic way would be more challenging than other generative image modeling applications.
So Jinsung, what has been the reception from people in healthcare to this work?
They're actually quite interesting. And after we publish our papers, and also we publish our blog post in Google, and the multiple healthcare centers are contacted to us, and how to utilize them, and how the impact of those works, and whether they can apply our method to their hospital as well. They are definitely eager to utilize recently very developed machine learning techniques to their own data set, but due to high regulations, so it is very hard to directly apply and directly connect it with the talent. But they think the synthetic data tools might be the breakthrough for those communication between talent and the data holder, that they can significantly improve the speed of applying this ML to the healthcare domain. Yeah.
So Sercan, earlier you alluded to the fact that healthcare is very regulated industry, right? So at what point what do you need to do to make sure that you can deploy this?
So it's definitely an iterative process that you need to get feedback from different stakeholders. and like you demonstrate, like there are different POC periods with different stakeholders involved, and you get feedback from them, and maybe you need to modify something in the method, or you need to explain something better, and so on. So adoption of such advanced technologies in industries like healthcare obviously take time.
So Jinsung, give us a sense of scalability and speed of these of the tools that you developed. So how much data can I take in, and how quickly can I generate synthetic data?
So we tried kind of two public data, which is called Mimic and EICU. And Mimic data is kind of, we handle 50K patients with lengths of stays that are going to be kind of 48 hours to 72 hours. And using that data, kind of, you can put 50K patient into our models, and we generate kind of similar amount of synthetic data within kind of 4 to 5 hours. And for EICU data, we use kind of 200K patient, kind of, it also does not take more than 10 hours to generate synthetic data from the scratch to train the model and inference. The entire time is less than 10 hours with the one GPU. But if you're using the parallelization, you can definitely improve the speed of the training as well.
So Sercan, the other thing about healthcare is you've got a lot of domain experts, right? So who have advanced degrees, potentially doctors, specialists, so and medical researchers. So have you kind of gotten a sense of whether they're comfortable with something that's a bit of a black box? So in other words, these people are used to using classic statistical methods where they kind of know the details of what's going on.
So one thing on our roadmap and ongoing effort is that, so at the moment we have our metrics for privacy and fidelity for the synthetic data, but we also want experts human feedback on the synthetic data, and they can compare with real data, and they can provide assessments on its quality and privacy. So that is one important piece that we think could help with further validation. I mean, at the end, I think that in healthcare industry, where decisions are high stakes and so on, especially for discriminative applications, explainability can be important. What you mentioned, like for example, if it's a disease prediction task, and if the user is a doctor, maybe the doctor will feel much more confidence in the machine learning model if the machine learning model is more explainable. But when it comes to synthetic data generation, I don't think that explainability would be that critical, because at the end, the output is a data set rather than a decision, and still explainable models can be built on synthetic data.
But they need to, if they inspect the data, they see it doesn't make sense, then they may lose confidence, right?
Exactly.
Yeah. So, Jinsung, give us a sense of, so is this something that you think other industries will be interested, or I guess more specifically, since you released the paper, have you heard from non-healthcare people?
Actually, I also have kind of contact from public sectors. They are, so, as you know, kind of healthcare also has some private data, but public sector's data is also highly private. So here, I think our method is not only applicable for the healthcare, but also applicable to any data set which are private, so it is hard to share directly. So I also contact from the public sector, especially for the custom part. And then they also want to generate synthetic data, and then they want to release those synthetic data to develop, for instance, anomaly detections in the custom, and those kind of machine learning tools they want to use, but due to the lack of expertise in their side and due to the privacy issues of the machine learning community, those are not connected well. But if they can use the synthetic data part, they can use the synthetic data as a bridge between this talent and the public sector's private data. Yeah.
And another big one would be maybe financial services industry, where there are a lot of regulations.
Yeah, I actually liked what Sercan mentioned earlier, which is basically this becomes some sort of middleware, even where you just synthesize the data and then no one touches the raw data anymore.
Yeah, I mean, raw data would be continuously updated, right? Like every day, new data would be generated.
But the downstream applications and users never touched the raw data so that privacy is always kind of observed, right?
Yeah.
By the way, as we close, I wanted to get an update from Sercan, because last year we talked about deep learning or neural networks for structured data in his project called TabNet. So what has happened since then? So set aside TabNet, but just in general, deep learning for structured data. Because I have to confess, I tried using TabNet. I used it a few times. It's a bit computationally intensive. Compared to other methods. So what has happened to adoption of deep learning or neural methods for tabular data from your perspective?
Yeah, we actually productionized TabNet last year, and since then we have received traction from different industries. Like, obviously, deep learning has more significant value propositions in large data regimes, and we also put a lot of engineering effort to make our implementation more scalable with the best practices from distributed training and so on. So if you have like these very large data sets, I think deep learning can become even cheaper than other standard methods like ensemble decision trees and so on, because deep learning can take advantage of the massive GPU, TPU pods in the ways that other traditional methods cannot. But that being said, I think that for small data regime, there are more challenges, like the deep learning models can be more prone to overfitting, and maybe the computational cost might be higher than, and sometimes much higher than, other traditional methods. So we had a few follow-up works, like for example, we had one recent work, interpretable mixture of experts, where our goal is to identify in what cases deep learning is really needed, and in what cases you can get away with simple interpretable models for some data samples. So I think that there's a lot of value in that kind of a direction, like understanding what kind of regimes can benefit from highly complex deep learning models and so on. And other than it, I think that like deep learning...
I guess, Sercan, there's the added advantage of there's a certain level of automation that comes with it, right? So for example, one area that structured data where deep learning seems to be getting explored and to some extent getting deployed even is time series forecasting, right?
Yeah, definitely. I mean, deep learning is being explored and deployed even without time series forecasting, like, I don't know, recommendation systems, fraud detection systems, stuff like that. I think that they are now being dominated by deep learning, but I think for time series forecasting, especially in large data regime, like let's say that you have many time series from many different products or many different locations and so on, the representation learning capability of deep learning can be very beneficial. And I think in the past 2 years or even past year, there has been a lot of breakthrough works in academia in pushing deep learning for tabular and time series data, and probably that will continue. And I think that as we have more advanced solutions, then I think we will see more and more adoption of deep learning in different real-world use cases of structured data.
So Jinsung, I'll let you have the final word. So on synthetic data generation, what trends are you looking at?
So you mean there are kind of what trends?
Yeah. What trends in synthetic data generation are you following and paying close attention to?
I think kind of definitely right now kind of we just focus on the tabular data, but extending to the text and image data is definitely one way. Another way is is kind of what Sercan said is kind of conditional generation. For instance, if we have certain information as a condition, how to generate the remaining information based on this condition. So in that case, I think, as you said, when we do data augmentation, we only can generate certain information, which is we only need, for instance, if we have a rare disease, and we can only generate the patient with the rare disease synthetic data instead of generating the entire data again and again. So two things. One is conditional generative model. The other one is kind of generative model in a multimodal way. Yeah, those are two trends that I'm following.
And with that, thank you, Jinsung and Sercan.
Yeah, thanks for hosting us.
Yeah, thanks for inviting us to here. Yeah.